Hello, MBA Physics. Today we're going to do the index of refraction lab. This is a lab that probably would take us 2 periods or more. So it's going to take a little bit to go through this. We're not going to do all the steps as we would have if we were here live in person. But it may go a little slow. And on your video screen, you should see in the bottom right-hand side a little gear. You can click on that and actually change the speed in which you hear the video. Or you can stop it. And it might be a little better if you speed up the video as we go through this lab. So this lab is going to involve light, and what we're talking about is that light will bend as it goes through a medium. This is like if you look into a fish tank and the fish don't look exactly where they should be, or you look into a cup and the straw is bent or cut in the straw. That's what this is about. So if we take a look at what our lab says to do, we are going to take a piece of plexiglass here, and we're going to draw around it. That's so that we know where it is. We are skipping the part of doing glass. Why? Because this plexiglass is easier to see with a laser. And so what I'm going to do is I'm going to shine this laser into this glass. And you can see, if I tip the laser back and forth, you can see that the laser enters right here at this point. I'm going to make a mark right there. Goes through the plexiglass and exits right about there and continues out to here. Now, you can see that if it were to follow this parallel line, it definitely does not stay in the parallel. It gets bent. When it goes from a less dense to a more dense, it always gets bent towards the normal. Then once it gets from the dense to less dense, it bends away from the normal. And it ends up being parallel if it's the same medium on either side. This is why when you go look through a glass window, it doesn't look like the picture is distorted in any, but it is actually moved over ever so slightly. So once we've got our glass drawn or marks made, we're going to take the glass away, turn off the laser, and we start the drawing part of our lab. So we're going to draw a line from where it exits, from where it enters to where it exits. This is point A, this is point B, and then we're going to go up here to where it came out, and that's going to be point C. Then we need to draw a line that is perpendicular to this, and I'm going to be very practical here and use this plexiglass to give me a right angle. And then I'm going to extend that right angle all the way through. All right. So what we're wanting to know is what is our angle here, which is our angle of refraction. It would be the same angle as it was over here. And this is our angle of incidence. It would be the same as if we came out on this side, an angle of incidence. In many ways, this is the angle of refraction. This is the angle of incidence. But whereas if we're looking this way. All right, then we're going to take a compass and make a circle. Can't be too big. All right, there's our circle. And then we need to do some measuring. What we're going to do is we're going to mark the distance. Coincidentally, it happened to come right here, but we want to draw a line from here to here and from this point to the normal. And that too needs to be a right angle. So let's use our plexiglass here. Give ourselves a right angle. And this is going to be Y, and this is going to be X and Y. All right? And then we're going to measure these things. So on our lab sheet, we would have done this one and this one, which is glass, which I skipped because it doesn't show very well with the laser. You kind of need to use your eyes. And we're doing this one, the plexiglass. So we're going to measure what is our X and what is our Y, and then our angle of incidence and angle of reflection. We're going to put that right here. So our X is about 3.4 centimeters. All right. And our Y is about 2.4 centimeters. Okay, I'm going to let you figure that out. Let's take our angle of incidence, and I need the protractor. I'm going to put this right on the line here, and we are right at 30 degrees. Wait, that was our angle of refraction. So that's 30 degrees. And our angle of incidence, which I drew on the wrong side here, angle of incidence is going to be about 44. So 44 degrees. This is 30 degrees. And our index of refraction is X divided by Y. That's from up here. And then our angle of incidence is sine I divided by sine R. Okay? And that's how we do that first part. Now, the instructions for our lab ask us to do some more drawings. And we're going to take our plexiglass and put some I'm going to draw the plexiglass here. And we're going to, the instructions tell us that we have to draw how the light can go through and have total internal reflection. And that's called the critical angle if you read your textbook. And what we can do is we can shine it at an angle such that it's so steep that it won't bounce out. There's no light coming out right here. So it actually comes here and it wants to bend away from the normal, and when it bends too far from the normal, it would go past horizontal to the surface, and so it actually bounces, and that's called total internal reflection. So I'm going to make some marks here, and you'll see that I can do this from multiple directions. So here we go. I'm going to make some marks. So here, that mark going to here, and then going out over here. It's total internal reflection. So the light is going this way, going this way, going this way, and then it happens to shoot out that way. Now, how could we use this? Well, it turns out that if this was long, and I were to shine it in here, we could make this light bounce forever. And that process we can put into something like this, and I can shine the laser in this tube, and the light will bounce around in there just like it does in here because it can't get out, and it'll go all the way through. So now you can see it comes out right there. Shines in right here and comes out right there. See, I'll shine away and it goes away. And all it's doing is it's doing exactly what this drawing is showing, and it bounces around inside there. And I can do it from this end going this way and shine it towards you. Okay, so that's pretty cool. All right, so once we've got this drawing done of the total internal reflection using the critical angle, we're going to play with this lens. We're also going to trace it, and it has nothing to do with this one. We're just saving space on the paper. And actually, I'll go ahead and go down here. As you can see, just like the lenses that we've talked about already, it takes the lines together and brings them to a focus. Before we do any more drawing, I want to show you what happens when we've got multiple colors. As we learned, red, green, and blue are our primary colors. And just notice what happens to the color when they all come together. You'll see that right there at that point, it is white. You can see that it's rather white there where they are crossed, and then when they separate, they're back to their separate colors again. All right, let's go back to the slits. And what we're going to do is, first of all, I'm going to trace around this lens because I'm going to draw the lines that go in and out. And the first thing we're going to do is we're going to shine right towards the middle of this lens, and I'm going to make marks that I can then trace out after I remove the lens. And with that much, I can draw all the lines. So I'm going to go from here. These are all straight. And then they bend inside of here a little bit. See how that bends just a little bit? As it's bending in the lens. Same way it was bending up here. But we are almost perpendicular. So the further out we go from the edge, the more bend there is. When we're in the middle, you'll see that there's almost no bend. Then from here, just like when we came out of the glass, we bend away from the normal. And that, if we think of a normal as the tangent line here, it's actually going to bend away. It doesn't feel like it, because we're all going to go through this focal point here. And you can see all those lines going through. Now, spherical lenses are not the best lenses because they work really well when all the light's near the center, but what happens when the light gets near the edge? Notice the lines are still parallel, but it's not coming to a nice, neat focus. In fact, you'll see that this line here, as I keep on moving it, gets to the point where it doesn't even come close to the focus and actually completely internally reflects, which you can't really see here, but it's gone. We only have 4 lines left. The 5th line bends so much it's actually coming out over here as it bounces around in here and comes out, just like it did in this drawing here. So the next drawing we're going to draw is this one. I'm going to trace the lens again, and we're going to make our lines And on the other side, so here we go with our parallel lines. And then they go through here. This unequal bending of the light so that it doesn't come to a focus as we get near the edge or the away from the middle of the lens is called spherical aberration. Aberration means that it makes it so that it's harder to see a focus and things aren't focused. And you can see that these lines don't all come to a focal point at the same point. And that's called spherical aberration. All right. What I'd like you to do is I would like you to sketch each of these drawings, and then finish the calculation for this lab here. You're going to calculate x divided by y and angle I divided by angle R and find the index of refraction for these two ways of calculating that. Then at the end of your lab, which I will attach this, you have some questions. What is the size of the angle of refraction if the angle of incidence is 0? Well, that question is talking about, well, what if we have a light that comes perpendicular what if the light has 0 angle of incidence? What if it comes straight on? It's not coming at an angle, it's coming perpendicular. Well, then what is the angle of refraction? Well, it will also be 0. What is the term critical angle? Well, that angle is the angle at which light is totally internally reflected. And probably better to show it to you this way. You see here, it'll actually go through the outside of the glass. But as I keep on going, there comes a point where it would be parallel to the surface. And once I get parallel, what happens? Total internal reflection. That is what is meant by the critical angle. Okay. Now, is it possible to get the rectangle to have total internal reflection with an external light source shining from a parallel side? What does that mean? These are parallel sides. Could I shine in here from this side to this side and get it to totally internally reflect? You see, as I get closer and closer to the angle of the critical angle, when I finally get to the point where it would reflect in here, it reflects over here. That is because I'm parallel here and it won't go out through the other side. So the answer is, it's impossible. Because as soon as I hit the critical angle for this side, I'm parallel on this side, because that's what the critical angle would be, parallel on this side. And if I'm parallel, I can't go in. So that's not possible. All right, and then with the lens widened, the rays all cross at the same point when they were shown close to the edge of the lens. This is talking about this drawing right here. So why doesn't it? Because when we get to the edge, we get spherical aberration, which each ray gets bent more and more as we get closer to the edge because of this angle of incidence and refraction. And so they will not come to a focus. And you should be able to look at page 511 for help on that. Now, why is it that when you look over the heat of a campfire and a heater, the objects on the other side look distorted? If you haven't done this, look on the other side of a campfire, and let's say you have a campfire here burning away, really hot, and you look across the fire. As you look across the fire, your image will get distorted. You can have the same thing happen on top, looking across a hot roof of a car or anything else that's hot. Well, what's happening is the air rising is less dense. And since it's less dense, just like something that's more or less dense, when a light ray goes through something that's more or less dense, it gets bent. The trouble is, over a campfire, that bending is very inconsistent. Unlike a lens that has a very nice, clean boundary, a fire, the air above a fire is all jumbled of different temperatures. And so when you look across there, the image on the other side kind of gets messed up. All right. So just a few more things I wanted to show you regarding lenses. This is, of course, a converging lens. And this one is also a converging lens. And I want you to notice that this one is the same as that one, but only cut in half. But you'll see what happens to the focal length is it's about twice as far. And then we can do some interesting things where we can combine converging with a diverging, and we can put the lines together and then we can break them back apart. And the difference is a little bit because of the spherical aberration we talked about. Otherwise we would have parallel lines coming out of here. It's also interesting that we can put this guy here, and you would think, oh, I'd make it keep on going apart, but as you get farther apart, you'll see it's actually bringing all the rays back together again. Again, because we're coming to the edge of the sphere, which is not a good lens. And then lastly, a little bit on reflection. This is a flat surface, and you can see you get angle of incidence equals the angle of reflection. And we can do a convex mirror, and you can see the lines are diverging, and a concave mirror that can bring the lines to a focus on the same side of the mirror. And that's it. Thank you very much.